Great. So I'm going to be talking about hacking Amiibo, which are these toys that Nintendo makes that interact with all their modern consoles. So you take this toy and you can like tap it to a certain place on the console. It interacts with the games. So like they can read and write data to them. So like in Smash Brothers, you unlock characters with these, and you can train them, and it like saves a profile to the toy. And the way that it works on the inside is it has a NFC. So it uses a NFC tag in the bottom of the figure. And NFC tag is, NFC is for doing contactless power and data transmission. And the NFC tag is basically an antenna and a very tiny integrated circuit that's powered over through the NFC. So I started looking at this in the middle of 2016, and I was really interested in like save file exploits like this, the one for the Wii that Fail Overflow did, where like you edit the horse's name and there's like a stack buffer overflow, and they have a whole exploit where they you load the file and it installs a new application to the Wii. So like the reason you find like exploits for games these days is to kind of jailbreak the consoles because you're not allowed to run your own code. There's also some fun ones on like the older systems where you actually can use an exploit to load in mods for the game, so you can create new content and like do a memory card exploit and load up a whole mod for the game. So at the time, only the 3DS and the Wii U were out, but the Switch was coming up, and an important thing is that the Amiibo are cross-compatible across all the consoles. So they're gonna anything that works on the 3DS and the Wii U it's gonna work on the Switch when that comes out later. And there's games like Splatoon 2 saves a bunch of data about your gear layout and stuff. So what I wanted to see, Jeff DeLay was actually speaking tomorrow. He said like, hey, someone should fuzz the data on the Amiibos and see like if you can do anything weird. So I thought it would be, if not the most practical approach, it would be hilarious to find like bugs on the Switch or something, or the 3DS, where you manipulate the data in the Amiibo and maybe find some kind of save game style exploit. So I wanted to find out like how easy is it to spoof these or edit the data on them, and could it possibly use it all on the Switch when that comes out. So the first thing to look at is what is the data like on the Amiibo, and if you just open an image of it, it's mostly indiscernible, just kind of random bytes. That it turns out some of this is plain text. So there's the serial number of the tag is in there, the character's ID is in there in plain text, but the rest of it is encrypted, and then there's signatures for the encrypted sections. So there's not much you can see until you figure out how does this crypto work and like what's going on. So like a brief overview of what I knew then is that each Amiibo is encrypted with its own unique set of keys. You can't just copy data from one of them into another, or copy it to like any NFC sticker that you want. All of these the data is also signed, so you can't tamper with it. And at that point, there were at least a couple of people who actually did already reverse engineer the cryptography and figured it out. And one person, Soccer88, had released this tool called Amiitool. Amiitool will actually do the encryption and decryption, but only if you have the necessary key file. So unless you get the keys out of the console, you can't actually use this. And they don't just like publish them online for anyone to download, because they don't want to encourage piracy on the games. So, and there were also things like they had an online API that would do this encryption and decryption for you over an API, but for that you need to get a key, and like they kind of watch what you use it for, and I would be rate limited by like how often I could hit the server, and the server has to be online. So I didn't want to do that. I looked at some of there's actually some cheat devices that let you like copy or edit Amiibo, but they do the same thing where they just have an online API and you have to be online. You connect this to your PC, and when you want to say like apply a cheat, it sends it over to the API and then gives you back the result. There's a pretty cool article about reverse engineering one of these, and there's like actually a bit of security built into this little $20 cheat device. But that was also not really going to be useful for me. So what can we do to like read or edit this and simulate it? So I figured that the best bet at this point was to do software-defined radio, where I could just kind of send whatever signal I want. So for RFID and NFC, one of the go-to devices is Proxmark, and you can reprogram it and like do whatever you want with that. And it can behave as one of the tags, so it can behave like an Amiibo. It can also behave like the console and do the reading and writing. So I can kind of simulate all aspects of the usage of the Amiibo with the console. And just to show you like what's going on in the tag, it has the little integrated circuit. It has some memory. It interprets commands that it gets over radio, and then it can return data. It can return stuff from the ROM or the EEPROM, and the Proxmark. Excuse me. So the Proxmark. Most of the code for the Proxmark is all like handles proximity ID cards and stuff. And all that I could really use here was some basic ISO 1443A simulation. So that all that is it does the RF modulation, and it does like kind of waking up the tag and reporting its serial number, and that's where it stops. So to do so this is like a data sheet from the NTAG 215, which is what's in an Amiibo. So all the stuff that's on top, like it will report its serial number, and that's fine. But all the memory operations and everything that happens after the tag is active, I would have to implement commands to do all those, so reading and writing, and password authentication. So to make a tool to simulate these now, so I know I'll have to have write a simulator for the Proxmark, get the crypto key somehow, and finally integrate those two together in some way to make like a really useful fuzzing tool. So the first part I'll go into is the crypto. So the 3DS was already jailbroken, which is a huge help because then I like all the games or services that would be encrypted. Now I can like get the decrypted version, and it would be easier to reverse engineer them and dump out binaries. There is a custom firmware for the 3DS that is pretty interesting that actually it had a debugger into the 3DS, but there are issues with it, maybe just in the newer versions of the 3DS, where the debugger, like the breakpoints don't work. So all you really have is reading and writing memory through this debugger. So like the interface, you can list processes. You can dump out the memory from those processes and read and write to addresses, but if you tried to attach to a process and debug it, it would crash. What I can do with that limitation is at least try to dump out the NFC service, see if I find the keys in the binary, kind of understand how applications and games use the NFC service, and also whether like if I put on an Amiibo and it gets decrypted, can I dump out the decrypted Amiibo from the memory of the service? And also do a little bit of static analysis of the service. So the first thing I did was use the 3DS homebrew library. It has a few API calls for turning on NFC and like reading data off the Amiibo. I set up a little app that would do that. So it starts up the NFC service, it scans, and it waits for an Amiibo to load. Once that loads, I dump out the memory of the service. And I was looking around in the memory, and you do find both the encrypted images of the Amiibo and also the decrypted image. You can start to see like the nickname and the names of the me that it was registered to and everything. They're all in plain text there, and to show the format. So now you can kind of see like what the format of the decrypted image is. So there's the nickname, the registered owner, game and application data is the biggest piece, and then there's the signature and the serial number, and some like flag bits and settings and timestamps for when the tag has been written to. So trying to find the keys that would let me just decrypt and encrypt these offline. Started with, so I actually was trying out Hopper to do this, and one of the first things to do is like you look for strings, and look for strings and immediately find this really weird thing shows up where I find these strings locked, secret, and unfixed infos. So I wanted to know, I suspected maybe they're related to the crypto. I wanted to know what they were. So, but on the other hand, I'm having issues with doing the static analysis because of the way the service binary is set up. There's lots of isolated stub functions for the different service calls. And also, the debugger doesn't work and have some issues with Hopper. So I didn't know what I could do. But then I decided using the Homebrew application and using the system call parameters that the people who make the Homebrew libraries had already figured out, I could have my app call into the service and maybe use that to identify code in the binary. So one of the things that happens a lot when you writing the custom app and you can get all these different error codes back when a function fails. So there's a very common one, which is the invalid state error code, which you kind of see all over the place, and it's this unique 32-bit value. So what I decided to do was I would replace this error code, and the first thing I did was just replace it with deadbeef and see, I call different functions, and if I see the error code deadbeef, I kind of know what code path in general that I hit. The second iteration of that was instead of doing deadbeef, I just put the address of where the error code existed. So I just overwrite all the error codes and overwrite them with the address where they are in memory. So then once I see an error code, I know exactly where it was triggered from. And finally, I just decided to set up a script where with the writing feature of the debugger, I would overwrite all the function prologues and just tell the function to return its own address immediately. So then I could put in select addresses, start pressing buttons to activate different function calls, and I would get the address of where that function lived. So what that looks like. Let's see. It's not showing up. All right, so there was just a video showing that, basically I press the buttons, I see the addresses. Once you get the address, you just look that up in the binary, and you can start to identify that code. So you can start, I found some code that will actually reference the unfixed info, key info, and I see it reads a special bit set by the kernel before it will select a certain group of that key info. And it turns out that what that bit does is it identifies whether or not the console is a developer or retail console. So at that point, I was pretty sure these are the crypto keys, and there's a different set for retail and developers. And then you can keep looking and see things like find an HMAC algorithm and certain offset in the key info is loaded and passed to this HMAC algorithm. It's like the HMAC key and so on. But I start to see where stuff in the binary is similar to stuff in a MeTool, but I really just wanted to find the keys and start using them to do encryption and decryption. So I did something kind of weird, and I started searching online where I formatted and encoded the information that I had in a certain way. I realized I probably shouldn't spell out exactly where to find the key, but it was pretty easy to just find that key using the information I had. And it turned out that I found the exact key file that you needed to use a MeTool. So, and looking at it, I saw there was stuff inside this key file that wasn't in it wasn't in the NFC service at all. So what I had not seen yet show up is the 3DS has its own dedicated hardware engine. And the way it works is the bootloader passes in these two different values to an AES chip, and it derives a new key that you can never get back out. So that algorithm was broken in a really good talk on breaking 3DS, but before that was broken, there was a different thing that you could do to replicate that encryption. So it's based on AES encounter mode, and AES encounter mode generates this, uses AES to generate like an intermediate stream of bytes, and those bytes get XORed with whatever your input is, and gives you some output, and the encryption and decryption works the same way. So an important thing with XOR, you XOR something with 0, you just get the same thing. So if you could tell the console, or tell the AES chip to encrypt a bunch of zeros, you just get this intermediate key stream out of it. And with that, you can do offline encryption and decryption however you want. So that is what was inside the AmiTool key file. And basically, without being given that file, you probably wouldn't have been able to set it up exactly the way AmiTool wanted it. But to figure out, yeah, so to figure out like exactly what parameters are being used, I wrote a Python script to draw out different things and then figure out that it was the hardware AES engine. But so using all that information, now I can kind of figure out how the entire crypto system for the Amiibos works. So there's two main partitions on the Amiibo. So one of them is called the lock secret, and that just contains the serial number and the character ID and a unique 32-byte sequence. And this is something that never really changes. The character and the serial number of the Amiibo doesn't change, so that's why it's called the lock secret. The data, all the game and application data and settings, that's in the unfixed info section. So the overview of what's going to happen now is so for each section, the lock secret and the unfixed info generate a set of AES parameters and HMAC keys using a random bit generator. And then using the HMAC key, you sign each section, and then after you sign it, you encrypt it, and finally you rearrange the buffer to store in the NFC tag. So the biggest or the most involved part here is actually generating those keys and the AES and HMAC keys that are unique to that Amiibo. So what happens is from the Amiibo, you take the serial number, the write counter, a unique 32-bit value, 32-byte value. You get the AES parameters and an HMAC key from the NFC service. It's going to use the hardware crypto engine to encrypt the unique 32 bytes. It's going to use the HMAC parameters from the NFC service to initialize the HMAC random bit generator, and it populates the seed value for the random bit generator with the serial number, the type of partition it's working on, and the bytes that get encrypted through the AES engine. So and then after it sets up a seed, the random bit generator does 48 bytes of output, which are going to be an AES key, a nonce counter for the AES counter mode, and finally an HMAC key. So this is what's used to do the signing and encryption for an Amiibo. So it has this whole set of unique keys, and also they change every time you update the data. So it's not just unique to the Amiibo. It's every time you update data on the Amiibo, it generates a new set of keys. So that's the crypto system. And so the next part, using that, I want to do the Proxmark simulator. So to start out, I just had sniffed traffic between the console and the Amiibo with the Proxmark, and took a data sheet for ntag21x and looked at like what the different commands are and what it's doing. So it has this procedure that the console always reads the Amiibo in the same exact way, and it writes to it in the same exact way. And I could start to pick out the functions that I needed to implement to replicate this. So that was going to be like the read, the write commands, the get version, password authentication, and everything that involved memory operations. So a lot of the work in working on Proxmark, like there's no developer documentation. You just have to read through all the code and figure out how it works and where you have to change it. So instead of doing like a really nice module for NTAG 2NX simulation, I just kind of tacked this right on to the ISO 1443A simulator that existed that would just do like, this is my serial number. You look at, so this is a close-up of the traffic dump where the console wakes up the Amiibo NFC tag, it gets the serial number, it gets some version information, it authenticates to the Amiibo because there's a lock for whether or not you're allowed to write to it. And then it starts reading out all the memory. So the first command to implement was get version. And all the get version does is kind of report what kind of NFC tag it is. So there's always the same set of bytes for NTAG 215. But one of the first things I encountered with like sending back data is you have to calculate a checksum, like an error checking checksum for the bytes that you're going to send back. And you also have to cache that because the reason you're using like a Proxmark or like special hardware for software-defined radio is you have like 5 milliseconds to read in commands and respond to them. So you have to do it very quickly, or else you time out and the session fails, and the console will try to start over. So to set up caching for different commands that happen early on, and then like calculate the checksum for them and put that in the cache. So the next command was the reading, and it's pretty simple. So the read it says what section of the tag it wants to read from, and you send back some bytes. But to do that, I would have to create some kind of memory buffer on the Proxmark where I could save all that data. So there's a custom malloc implementation on the Proxmark, and there's a useful section of that memory that's just for holding a buffer for like cards or like tags, where even if you free all the other memory in between the different operations you're doing, it will retain that memory for you. So using the big buffer malloc implementation on there, I could store all the bytes to represent the EEPROM on the tag, and read or write to them from there. And another useful thing is that you could use USB commands from the Proxmark client to read and write into this buffer. So fast read is similar, except that you can read an arbitrary number of pages all at the same time. The write command will just update 4 bytes, so it tells you where to write them. You update those 4 bytes in the memory, and then there is password authentication. So simulating the password authentication, I don't really need to tell the console like, oh, that was the wrong password. I can just always accept the password that it sends in. But I thought it would still be interesting to figure out like how the password works, because it's set up where if you want to write to the Amiibo, you have to authenticate with the password, and if you use the wrong password 7 times, it will permanently lock out the pages, so you can never write to them again. And that's a security feature of that NTAG. And a fun thing that you can do using the Proxmark is actually, it's pretty easy to figure out how this password works. So using the Proxmark, you can kind of specify any serial number for the tag that you want when the console is trying to talk to it. And if you put a serial number of all zeros, or the first byte is it's always a 4, so that just gets ignored. So basically you put in all zeros, and you get back an interesting password of just AA55, AA55. And then if you start putting like AA and 55 bytes into your serial number, one by one, you start to see that it zeroes out the AA and 55 in the resulting password. So it's probably, you can tell it's probably an XOR operation where what you're doing is canceling out the AA and 55 bytes. So you keep going with that. If I start to move a byte that's just FF and I drag it across the serial number, In the password that I get back, I just mask out the AA55. You very clearly see that it's just copying that byte. That byte shows up in the password in pretty much the same location until you get to like the third one, and then it has a shadowing copy of that byte that's following behind it. And then doing some more tests, like I put another byte in my serial number that shadowed that one, and it zeroed out the shadowing byte, and then I put one ahead, and it zeroed out my original FF byte. So you can see that it's copying bytes from the serial number and also XORing them against each other at different positions. So that the algorithm that it's using is just this. It XORs one byte of the serial number and then a byte to ahead, and then the XOR mask. So now if I need to, I can accurately simulate the correct password, or I can write to a real Amiibo using this. So once I had all the commands implemented, I wanted to integrate the Amiibo cryptography into the simulator somehow. So the Proxmark client, it's all in C, but it lets you write Lua scripts, which is going to be a lot easier to deal with. So I took Amiitool, which already implements all the cryptography. I put a Lua wrapper around that and put it into a Lua script, where from the Lua script I could load up images of Amiibo into the Proxmark, or I could also dump images out from an Amiibo and save the state of a simulated Amiibo. So if I want to like simulate one, stop working with it, and just save it, and then bring it back up later after I change it, I can do that. So what I have, this is kind of how it looks, where you have the Amiibo script. You can very easily manipulate the image however you want using the crypto from Amiitool, and then send it over to the Proxmark to simulate. So that's the simulator. But finally, the switch comes out. So this all worked very well on the 3DS. But finally, the switch comes out, and for some reason, it's not working when I try to talk to it. So turns out that the switch, and also the Wii U, but I had not tested on the Wii U before, but they read a signature from the tag where NXP signs the serial number of each tag, and there's a signature that's burned into the integrated circuit, and it will check this. So which I'll get back to you later. And also the antenna that comes with the Proxmark, it's well suited for ID cards, so it's like a rectangular shape, same size as an ID card, which is good for like the 3DS, and it kind of worked on the Wii U, but it was not working on the Switch. So this was not going to be useful on the Switch just yet. So the antenna, it happened to work very well in the 3DS because the dimensions of the antenna in the 3DS looks a bit like an ID card. It's kind of the same shape. But in the Switch, in the controller for the Switch, the antenna is like the size of your fingertip. So it was very difficult. You would have to kind of sit there with the antenna and have it retry over and over again until you were lucky enough for a successful operation to happen. So the official Proxmark guide is like if you want to look up how to make an antenna for this, they kind of tell you take a cable and rip it open and start coiling it around, and you manually will like tune it to get the correct tuning for which I thought was like, I didn't want to deal with that. What I wanted to do was basically get a cable and buy a pre-made antenna and just see if I could use that. It turns out that you can't just do that. So when I started it up and I tested the tuning, and it had like a really poor signal strength. So it turns out an antenna for NFC is actually a circuit of inductor and a capacitor, and they have to be matched in a certain way that they'll have a certain resonant frequency, which is the frequency you want to communicate on. So my antenna was not matched up to the capacitor that was on the Proxmark. And I kind of tried to save this, so I looked up you have to look up the inductance of the antenna, and I calculate like what capacitance I needed to get this antenna to work, and using another formula to figure out like, can I add more capacitors onto this to make it work, and like calculated what capacitors I could use. So it turned out I took like so it turned out I needed something like an 11 picofarads capacitor, but I tried to splice in this like crappy 10 picofarad capacitor that's not really for RF, and it did work with the Amiibo. Like it was able to talk to the Amiibo, but it still wasn't good for the switch. And trying to make an antenna that will actually work, you need to get like better capacitors that are designed for RF, and they're very small, and it's difficult to work with. So in the end, I learned like that's why they kind of tell you to just take a wire and coil it around and like manually tune it, because then you can tune it exactly to your Proxmark to get it to work. The alternative is make a circuit board antenna where you have to figure out the design of it, and it has to match up exactly with the capacitor on the Proxmark. So I did not finish making that antenna yet, but when I do, I'll post the design for that. So the other thing was the signature check. So the end tags have elliptic curve based digital signature that they put in the tag. It signs the serial number, and it sounds kind of weird just to sign the serial number, but it prevents you from making new new tags with whatever serial number you want, and also all of the Amiibo data is bound to a specific serial number with the signing that Nintendo does. So you can't just start creating your own Amiibo this way. And the problem for me with not being able to just use any serial number I want is that there are some games where, like Breath of the Wild, each Amiibo you're only allowed to use one time per day, and it would do that by checking what the serial number of the tag was. And in general, I just wanted to be able to use any data that I wanted. I didn't want to be restricted by, say, only using serial numbers where I had that signature for it. So it seemed like I wasn't going to be able to do that, but it turns out, I started to look into it. So the cheat devices, I noticed some of them had cheats where they said they would cycle the serial number for you, and I didn't actually look at them to see what they were doing, but because they use that online API, you can guess that they have the capability to just harvest all of the serial numbers and signatures for everyone that uses an Amiibo on their device, which I thought was not going to be a realistic thing for me to look at. I did try to see if there were any crypto errors. So this elliptic curve signature they use, the same thing was used to sign games for the PlayStation 3, and Sony screwed that up by reusing a nonce. And if you reuse the nonce in this algorithm, you're going to leak the private key. So I tried to see with a few signatures that I could look at. I parsed out the different values and see are they using the nonce anywhere, and it turned out that they did not, at least in the small sample that I looked at. And then finally, I tried to see what I could do messing around with the Proxmark. So the entire process for when the console wakes up the Amiibo and it reads it is going to be this. It will get the serial number of the tag, it will get the signature, and then validate the serial number with that signature. After it validates the serial number, it asks for all the memory, for the entire image. It generates keys using the algorithm we talked about before, and finally checks the HMAC signature of that data. So those are all the steps. So there, if you kind of maybe guess, there's a problem here where it does not correlate validating the serial number with checking the image and checking the HMAC of the image. So on a real tag, you wouldn't be able to do this, but with the software-defined radio, you report a certain serial number when the tag wakes up, where you know the signature for that serial number, and then after you pass the serial number verification, you can send back the image of any Amiibo you want afterwards. So that you see the serial number and the signature I sent at the beginning do not match the serial number that's in the memory that I send back afterwards. So using that trick, now I can just do I can use any serial number and signature that I know to load up any Amiibo image I have or create. I did finally report this to Nintendo. So they fixed it in the 5.0 patch on the Switch, but they said that for some reason they could not fix it on the Wii U, which was interesting. But now without even doing any crypto operations, I can just use any image of an Amiibo that I want to. So finally, I kind of have the simulator that I want, and I can start simulating the Amiibo. So this is, let's see. Okay. All right, so here's the video of using it on the Switch. So, sorry. Okay. So I'm going to speed up through parts where it took a long time for the antenna to work, because I did not make a new antenna that's better for this yet. But so you can see in the console on the bottom, I load up an image of a Link Amiibo, and then what I'm going to do is it's a fresh Amiibo, and I want to register it. So I'm going to write pick a me to associate it with, and then write a nickname for it. And this is just going to demonstrate that I can read and write. So I can write back to it, and it persists the memory, and then after it registers, I'll load it up again to show the nickname is still there. And finally, so it registered. The data's been written back. And then, so I load it up again. You can see that it has been saved, and it loads that nickname I set. And then just to demonstrate, so you can't actually see, but I am using the signature bypass trick here to use one image with a different signature and serial number that's not actually associated with that image. And you get this horse when you load up the Link Amiibo in Breath of the Wild. So that's the demo for using it on the Switch. Okay, so the future work is fix that antenna. But I did start looking at some of the new games once the Switch came out. And for example, Splatoon is pretty interesting in that it saves a whole layout of all your gear and settings are saved into the data section. But it turns out that with the newer games, they've added another layer of encryption for all the application data. So to figure out that layer of encryption, we have to start reverse engineering the games, which now that there's a bunch of exploits for the Switch is going to be more feasible to look at now. And then maybe set up a better harness for actually automatically testing instead of manually going back and forth between the console and the Proxmark each time you want to test something. But all the code, so if you have a Proxmark, all the code is going to be made public at this link. It has a pre-built wrapper for the Amiibo tool, but if you want to compile that library yourself, that code will also be available on GitHub. And then I gotta say thank you to Jeff DeLeo and Nolan Ray for their help with like answering questions about things like the 3DS debugger and the antennas. So that's all I have. All right. So any questions? Thank you.
You guys know the drill. Raise your hand if you have a question.
All right.
Don't be shy, we still have a lot of time for questions.
Oh.
I'm just curious how long this took you.
To get it working, I'd say like to get it to work on the 3DS, it was maybe like 3 months of kind of working on my off time to reverse engineer the NFC service and also program the Proxmark. Like a lot of it was, like I said before, there's no documentation for development code for the Proxmark, so I had to like figure out where to put things and how to how that source code worked. So and then after that, when the Switch came out, maybe another like week or so on looking at stuff for the Switch. So.
Well, then I have also a question maybe.
Okay.
Would it be possible to, instead of using the Proxmark, to do it with a normal smartphone? So Android is also capable of emulating ISO 14443 tags.
Yes.
So apart from the UID, I know Android cannot emulate an static UID.
Yeah, so I didn't talk about it. Some Android phones have NFC emulation, but it's kind of locked down. So if you get a rooted Android phone that supports this, it's possible to do some NFC tag emulation, but I think you also need to kind of rewrite code for the NFC. So I think somebody has done something like this, and you have to actually program it. You have to write the code for the phone to do this. I thought it would be easier to just do Proxmark, where like I can just edit the source code directly, but it would be fun to just do it from your phone too. So.
Okay. No more questions? Then,
All right.
Thanks to speaker again.